This video is intended for entertainment and historical purposes only. It's not meant to be an instructional tutorial or provide professional advice. Today, we're going to be in the machine shop fabricating new main connecting rods using a very unconventional technique. Most steam locomotive connecting rods were hot forged by a team of blacksmiths using massive steam hammers to form the hot metal into rough connecting rod shapes. This process aligned the grains within the metal and created a very strong and durable product. When the forging was complete, the rods looked something like this. This is an original, new old stock connecting rod from H.K. Porter. As you can see, it's never even been machined. The forgings would then go to the machine shop, where they would be turned into complete, usable rods, which look like this. These are original H.K. Porter main connecting rods from a 2-foot gauge Dinky similar to the Davenports. These connecting rods aren't fancy, and are basically made from something akin to mild steel. Later, manufacturers used very exotic materials and techniques to produce incredibly complex and lightweight rods. The Dinkies have more in common with a steam shovel than they have with these complex mainline steam locomotives. Welding on existing steam locomotive rods is a real no-no, except for in special cases with proper approvals and following approved standards. But that's a whole nother conversation. Fabricating Weldment rods is allowed, but there are strict parameters and standards which need to be followed in order for them to be safe for use. This isn't something that can be done willy-nilly. We find the process of making Weldment rods very intriguing. The Dinkies are never going to work for a living again. They aren't going to keep a schedule, and they'll very likely never even hit 10 miles per hour, which is only 140 RPM. So because we can, we're going to take this opportunity to fabricate Weldment rods just to see how they actually perform compared with an original rod. Then, after a year or two of use, I'll inspect them for deflection and have them x-rayed to see if any flaws have developed. Prior to doing any of this, we established the maximum potential stresses that could be placed on the rods to ensure copying the original design would give us an appropriate factor of safety for all the welds and materials involved. And for the record, the weakest point of the new rods will far exceed the maximum stress they could ever encounter in service. Those of you who want to see the hour-plus extended video, which goes into much more detail, you can find it on my Patreon page or in YouTube memberships. Now, let's head into the machine shop and start making those main connecting rods.
So this is a discussion about main rods. We've ended up with two 7x12 Davenport locomotives, and out of both locomotives we have one original rod, which is this one. You can see the pitting and the corrosion and the forge marks, and it was pretty roughly made in the forge. This end was badly corroded, the bolts were corroded, there was no key, there was no brass, the strap was kind of a mess. So before I knew we had two engines to do, I thought I only had to do one rod. I manufactured this rod, which is a twin to that one for the other side. Now I've got to make two more. So I'm going to take you through the process of making rods, brasses, fitting, tapered bolts, all sorts of good stuff. At one time, there was a major admonition in the maintenance manuals for steam locomotives that rods weren't weldable. Well, it wasn't really true. What they didn't want was Johnny Stickum together in some field roundhouse getting out his Forney buzzbox welder and some kind of jet rod and trying to fix a cracked rod, which would have been disastrous. But at the back shop, they welded on rods all the time. They built up surfaces. Now, I'm talking about in the 40s and 50s now, and welding started just after the First World War and was pretty crude, but as time went by, more and more processes were used and more welding was used in fabricating and repairing parts. I just finished working on a 1928 locomotive built by Baldwin that the dome course was butt welded electrically. So even then they were starting to experiment with welding boilers. So this is what I'm making it out of. This is a piece of A36, which I have on the other end. It's a piece of the same material, which I have a mill cert. I have a mill cert for this bar, and I have a mill cert for the material that I make the straps out of. The point of welding, electric welding, is you need to have the correct procedure and you need to know what material is. Well, this is just A36. It's simple procedure, little preheat, little post-heat, or in my case, this rod went through, was thrown in the stress relieving furnace along with some boilerplate. And there's no reason not to build these up. Use this block to make this piece at the end. I'm going to manufacture straps up, and they're going to be welded down at the end here. They're welded here and here. And the other end of this block will be used at this end for this piece. And these are two short pieces of strap that are welded here, and this is a machine portion that's welded again. And you can look at it, and you can look at it very closely, and you will see that you cannot see any remnant of a weld. It's been machined away, and it's 100% weld. And it's every bit as strong or stronger than the original. So we'll go through this procedure, how to make tapered bolts, how to machine brasses, all that sort of thing. This series will be, it's quite a long process, but it's kind of interesting in manufacturing new main rods for these locomotives. I think this is the prime reason why the second locomotive wasn't restored originally, was because the rods had gone missing. The crows probably walked off with the brasses thinking there were big lumps of brass, when in fact they're not very much, they're all hollow. So I hope you enjoy this. So the first step is to cut up the blocks of material for the main rods into two pieces, one for the front, one for the back. And we'll just engage the machine and let it gnaw away at its own time. And it'll eventually chew through that, and then I'll end up with two pieces I can use. So the first item of business is to disassemble the original rod, the original main rod, and remove all the components because I'm basically copying it again. Get the brasses out. This brass is in one piece because I really don't know what the centers are yet. So if you look carefully, you'll see that there's a center here. I've drilled a hole to make it convenient, but these two pieces are soldered together. So it's one lump. Eventually you melt them apart, but I don't know what this hole size is going to be or exactly where its center is until we figure out the clearance volumes on the cylinders. So we'll take this out first. So this end is put together with a key, which comes out. Take the set screw out of there because you'd catch your hand on it. The purpose of the set screw is to hold the key from moving once it's in where you want it, and to remove the two tapered bolts. These are tapered and they're supposed to be there. You see they don't go all the way to the bottom, but when you actually put this together, finally you hammer these down and it makes a very tight fit for the bolts in here. So we'll take this apart, take the brasses out. So here we are with everything apart. We got the tapered pins, the wedge, which sits in a slot here at the end. Its purpose is to tighten the brass. It bears against this piece of plate, the brass itself, and the strap. The brass is still soldered together. You make these in two pieces. You can see what I said, that people think it's a big lump of brass, but it actually isn't. There's not much to it. So we'll show you later how to make these, but I've left them soldered together because I don't know how well fit on the journal is going to be, or where the clearance volumes. The clearance, this is the only place that you can adjust the clearance volume on the cylinder, and that's on the steam cylinder itself. That's how the clearance volume is, how close the piston comes to each cylinder head. And it's supposed to be shy of each cylinder head by a certain amount, and you have to balance that. And the only way you can do it is by shimming this brass back and forth within this strap. And so, not knowing where that is, I may have to take more material out of there. I don't really know. So until we go to actually fit the engine up, we'll just leave it all together like this. So the first item of business is to manufacture this block to this dimension and mill the tapered slot in it. It's easy to do because I can shape it in the mill and I can stand it on end and I can cut that slot in here really easily, and I'll do that for both machines. And I got the rod apart because I need to make all the measurements that are going to be here. Now this is the wrist pin end all apart. Got this brass made up, it's still soldered together. You can see that the back of it is sloped. Match this wedge, which this bolt moves up and down to tighten, take up the wear in the actual brass itself as the engine matures. So we'll have to copy this. So we're working on getting components to make this strap. These are the blocks that have been machined up. They represent this piece. And over here is the other one. It's the end cap, the two side straps, and basically these are clamped together. And this is positioned carefully with a gap. And welded. This is 100% weld here and here. The reason for the rounded end here is because you don't want the weld to go onto this piece. And this is actually in backwards. This is the actual end that's going to be used when it's all finished. One thing I should say about the material, this is going to be the middle of the connecting rod. These are the straps. And there's an old rule for Boilermakers and for high stress products that you always put the stress parallel to the way it's been rolled. So this has been rolled in this direction. These have been rolled in this direction. These pieces have been rolled in this direction. And so when I weld them together, any laminar inclusions that might be in this steel are not crossways to the stress. They're in line with the stress. When you build locomotive boilers, you have to be careful that you roll the sheets up into a circle for the barrel in the same direction that they're rolled. You can't go crossways. So all of these pieces are being put together in the direction in which they've been rolled. So again, this has been rolled this way. This block has been rolled this way. The little pieces that are left over are on the other ends. The bolts have been rolled this way. So when it's all welded together, there's no cross laminations in the steel. So this is the get-up that we're using to weld the straps together. We've got the block in here. That's going to be the end of the connecting rod. This end is milled very square. It's also been radiused so that we don't end up gluing one to the other. If you can see, there's a radius there. So when I do my first weld, which is a full penetration weld in here, it won't weld to this block. There's a bit of a gap there. So this block is very much centered on the end and both sides, and it's just a matter of putting it in the welding vise and doing the first pass with 7018. The slag will go on the inside. It'll fall inside and protect that block and fill that space, and there shouldn't be much of a space left. So this is the first pass with 7018, a 3/32 rod. Fairly high amperage because you want to get right through the crack, but you do want to spill over the ends. The problem here is that this material is the same width as it's going to be when it's finished, and normally I use wider material and mill it all off. So you got to make sure the weld overhangs really well on both sides. And around here we've done a second pass with 3/32, again making sure that we've overlapped here on both sides. And now we're going to finish the rest of it with 1/8 7018. Well, as you can see, we're progressing with multiple beads of weld, making sure that the weld spills well out on the ends because we're going to have to mill this off. Again, I was unable to buy wider material. These days it seems to get worse and worse. There's not much selection. These are too thick. These are 3/4. I will eventually mill them down to 1/2 inch wide, and this will be 5/8. There's the weld on the other side. So these are the straps that have been welded. They've been stress relieved, and the ugly overlap here has been milled off just to make sure that we've got 100%. And the mill scale has been removed, and you can see the weld is complete. I got a little gob there to take off with the die grinder. Just sweeten them up a bit. So what happens now is these are too wide, 30 thou too wide. And these are supposed to be 1/2 inch. These are now 5/8. And so I'm going to weld this piece. This is the end of the rod, will be the end of the rod. It's going to get welded up in this position somewhere. And just down at the ends, rigidly welded, and then I will machine everything up. The outsides, the sides, so I will drill and tap, or drill and ream out the tapered pins, the tapered key, and the lubrication hole. Everything finished, completely ready to go before I cut the welds off, as this is too long. As you can see, here's the original. It has to be all removed down to this size and made correctly. So the next step is to cut the keyway, tapered pin keyway across here, and now's the time to do it. So we're getting ready to mill the slot for the key. It will be in the end of the connecting rod. This is how I line it up. This key is up against the square part of the mill, and it doesn't move, so this angle has to be correct. Once I mill the slot, the key actually goes in the other way, and so when it's parallel, it pushes on the brass correctly. So this is what we're trying to accomplish. This slot is for the key. There's a set screw to lock it here, and the key just sits in this slot and pushes on the brass. And as the brass wears, you just keep feeding it in. Eventually you put shims in the bottom of this slot to keep, and shims behind the brass. This is the original rod, original strap. And these are the two replacements. They've been welded together down here to keep them as one unit. Now I have to machine this 3/4 inch thick material down to 1/2 inch all the way around. And I have to put in these tapered bolts and the holes for the key here. I've already got the slot milled in here for that, and the lubrication hole, which is up here. So the first step is to put these two in the shaper and machine them down to finished size. As you can see, there's absolutely no differentiation between the original steel and the weld, because the whole weld has been stress relieved or annealed, and you just can't tell where the steel is anymore. It's all the same strength, all the same material. So we're going to do this for all four sides, get down to 1/2 inch, and then we'll move on from there. The chips that come off of this thing are guaranteed to stick in your shoes. So we're doing the end of the strap. Going to take it down to 9/16 as per original. Taking a really light cut because it'd be easy to flip this out of the vise. So this brief discussion is about tapered pins. I'm at the point now where I have to put in the tapered pins that go through here. In original locomotive work, most tapered pins were 1/8 of an inch per foot taper. And some cases they also used 1/16 of an inch per foot taper in various places. This was so that the bolt could be driven home and would not be allowed to move. Nothing is tight, but it's still removable. Well, in this case, this original rod, the bolts were badly corroded, and so when I went to make new ones, I discovered that these pinholes were 1/4 of an inch per foot. That's a standard tapered pin reamer. That's like this. Now, 1/8 per inch per foot tapered reamers and 1/16 inch tapered reamers are no longer made. You have to have them custom made. They're very expensive. And so a lot of times through the course of the locomotive's life, when it got rebuilt, as this rod was, these pins were re-reamed to 1/4 of an inch per foot taper because these are all available. You can go down to your local supplier and get them. This is a number 9. So I'm going to just follow through with the 1/4 inch per foot reamer, even though they're supposed to be 1/8. But I don't know that it really makes a heck of a lot of difference. Now, when you're making bolts and tapered holes and pins, there's always the question, it's called the chicken and egg situation. Do you make the pin and fit and ream the hole to fit the pin, or do you make the hole and machine the pin to fit the hole? It's almost impossible to make unless you're using NC tooling, it's impossible to make these pins exactly the same. Every one is slightly different. And so what I do is I make up the tapered bolts, and then I ream the holes to fit the bolt. On all locomotives, you'll find that these are numbered. Each one has a number on the head. The strap is correspondingly marked because they're individually fitted. I can show you here that this is where this pin is in the wrong hole at the moment because it goes all the way home and this one doesn't go close. So, and if I interchange them all without knocking this whole pile down, you will see that this pin fits correctly in this hole and this one is correct in this hole because they've been individually fitted. The same applies to these. And when you fit these bolts, you try and reach about a half to 3/4 of a diameter proud without them being driven home, because they get driven home at the end of the day. And that makes them fit really tightly in the holes here and here, and doesn't allow this strap to move whatsoever. And yet, you can hit them on the end. That's what this relief is for, so you don't damage the thread. You can hit them on the end and they will come out to service the brass, of course. So these are the roughed out bolts. They're turned up to 5/8, which was just shy of just a little bit more than this portion. We're now going to turn them between centers to get a taper. Again, everybody does things differently depending on what tools they have, what their life experience is. I don't have a taper attachment, and so I'm going to turn these between centers with the dog with an offset tailstock on my little lathe to get the taper. It involves a fair bit of fiddling around to get the taper right, but once you get it correct, it's just a matter of turning them out. One of the things I should say is that, again, when you're making these things, you got to figure out a procedure in your mind what to do first. For example, you can't turn this thread once this is finished because this is a tapered surface and won't fit in the chuck. And so what I did was I actually turned down these ends and I threaded them and finished them before I did this portion, so that when I'm done with the taper, I'm all done. I don't have to mess around with trying to put tapered things in the chuck. The other thing is, if you're trying to power thread, just holding on this little tiny end, this gets wobbling around pretty bad. So again, you just got to figure out the procedure in your mind based on your experience, what your skill set is, and what machine tools you have. So this is a raw bolt. This little piece on the end that's bolted on, it's called a dog. It's just set screwed on, and it's put in, it drives it with the faceplate and between the center on the other end. This is the old way that they used to turn all the time. They didn't have fancy chucks. Every lathe came with a faceplate. Doesn't matter what size lathe, this is how they turned long shafts. Of course, you better watch out for the dog because it's a wicked sucker. It can drag you into the lathe. This little guy will do you some damage. It won't kill you. It doesn't have enough power, but a big lathe will wrap you right up onto the shaft. So you have to be careful what you're doing. So what we're going to do now is we're going to fire the lathe up, and we're going to start taking cuts off of here, and you will see that the cut will basically peter out because now this is square. This has been turned in the lathe. This root diameter is roughly a little bit more than the root diameter of the finished taper, and so we're going to start making passes. So I'm just engaging the half nuts and letting this machine drive itself along. Yeah, this is a small machine, but I've turned a lot of bolts in this. There it is, it's running out of material. So this part is the correct taper, this part is still parallel, so we have to go back and take another cut. So here we've taken it out of the lathe. The dog, the piece, nothing's been disturbed. It's been working between these two centers. And just to make sure we're in the ballpark, you offer it in a hole and it goes down tight and loose. It should not rattle. You shouldn't be able to get rattle in this end or this end. There's no play in this, and so the taper is correct. It's a little bit proud yet, but maybe another cut off of there. Again, these dogs are dangerous. They can really hurt you. I really should have a much smaller set screw on this, but nonetheless, they can grab you. But this system sure works. So we're going to put this back in the lathe, and it'll be exactly where it was before, and take just another skim off to make it slightly smaller. So here we are. We have the finished turned taper. It goes in the hole, in this hole, about the right direction, about the right amount. And to fit this, you see it comes up short, but when you tighten up that nut and you give it a tap with the hammer, it goes home. And nothing can move. It's completely fixed in there. I still got to finish the heads and pretty it up a bit, but these are pretty much done. So we're going to cut a couple of wedges for the big ends. This is a piece of 3/8 plate. I've got an original wedge in here to give the angle, and it's just a matter of gnawing this off. One on an angle, one straight, gives me 2 wedges. So we'll just let the hacksaw do its thing here. This is at the maximum amount this hacksaw will handle, but it doesn't seem to have any trouble with it. So here we've got the completed big ends for the Davenport, the second machine. They've all been machined all over. The bolts have been fitted. They're not quite driven down tight, but they're there. The slots for the key have been drilled. It just got to be filed a little bit. The only difference in Davenport rods is between left and right is the position of this set screw. They're both face outwards for obvious reasons. Therefore, this is the right one with the set screw here, and the left one's there. Other than that, they're completely interchangeable. They're exactly the same length, same width, same everything. These are too long. They're going to be cut back to here. And this block will eventually be welded onto the rod. So we're getting started on making this piece here. 2 of them. To that end, I've got 2 2x2 blocks. Slices off a 2x2 mild steel bar. I've tack welded them on both sides all the way around, and I placed a 7/8 bolt. I drilled a 7/8 hole, placed a 7/8 bolt with a center in it, and I'm now going to put it in the lathe and turn the outside diameter of these. So here we are with the finished blank. It has to be bored out. It fits this. I mostly wanted to show you the heat effect zone from the weld. You can see where I V'd it out. I didn't try to keep the weld back as far as possible, but you can see the heat affected zone, which happens when you don't preheat and post heat and all the rest of the stuff that you're supposed to do with these parts. If I was to stress relieve this now and give it another cut in the lathe, this would all disappear. That hardness would be gone. And bear in mind that this is much wider than it needs to be. So those those heat affecting zones, they get machined away. That's why I didn't bother. So the next step is to bore this out to this internal diameter and break the 2 pieces into halves. You can see that it's almost impossible to see the line, but these are 2 precision halves. They will be exactly the same. So here we are. We've machined these into 2 pieces. They just came apart when they came out of the lathe. So we're at the next step. I'm busily making all the little bits and pieces that are going to become the eye. We have a base block which has been accurately machined so that the wedge will slide on it properly. We have the side pieces made up. They all have to be V'd so they can be welded. But I've made up a slug. This middle piece is called a slug. Its purpose, this is exactly the size of the eye that's up here, and this will hold everything in position while we do all of the welding. What'll happen here is that this is laying flat on the bench right now, but it actually comes up halfway, and it will be all tacked together like you see it, only this will be weld prepped. They'll be tacked all on both sides to hold it rigidly in place so it can't move. Because when you start to weld a small item like this with a lot of welding, the weld will pull in all directions that are pretty hard to calculate. And so you depend on the slug to hold the inside, which is what we're worried about, in exactly the position and the size that we want. At the end of the day, when the welding's all complete, this will be full of stresses. It'll be very tight. There'll be a lot of, and we'll heat it up red hot and cool it in air and allow everything to normalize down so that all the stresses are gone and everybody's happy with everybody else. We won't be able to drive this out. This will still be very tight, but you just drill them out and get rid of it, and you'll end up, this will be machined all over. It'll be down to size. This is 1.5 inches, by the way, and this is 1 3/8, so I got something to remove. And we'll end up with a nice weldment that this part up, that will be the eye, one solid piece of steel. So here we are with the welded up pieces prior to stress relieving. We're just knocking them down so that they have the same section all the way around, and then we'll soften them up before we do the milling, save the tooling. So I've gone ahead and begun machining these pieces. After they had fully cooled to room temperature, you can see that these corners were V'd out so that the scale or the slag from the weld would go in and prevent this piece from being welded to this, which makes things difficult. The rest of the weld is invisible. It's complete. It's called 100% weld. It's now, this is one piece. This is not any separate pieces anymore. It's all considered to be one piece. I have machined this width down to about 40 thou over, and I've put these pieces in the shaper just to take the rough weld off. Again, you can't see the weld at all, and the shaper will show it if it's there. And that's so I can grab it in a vise to drill it out. So I've drilled a line of holes down through the whole slug, and now it's just a matter, this will collapse inwards, it's just a matter of driving it out. So only having two hands, I turned the camera off and drove it down a little bit, and the rest of it just drops out the bottom. Like that, this piece will just fall in. And there you have it. So these are the three rods together. They've been very carefully lined up, very carefully fitted. There's spacers down in here that represent the gap for welding. The other end is the same. They've been made sure that everything is exactly correct. So now what I'm going to do is take all of these pieces and put them in the shaper and weld prep them by cutting a 30-degree angle on here, both sides, the other end as well, and then proceeding to weld them. So these are the welded rods. What I did was I V'd them down to 60 degrees, both sides here and here. I put in root pass with 60-10 just to get a nice root pass and cleaned it up, and then everything was welded with 70-18. So these are fairly straight. We'll finish them off just in the hydraulic press. As you can see, these are way too thick. These have to be machined down to 7/8 and profiled, and this neck is quite a bit narrower, and we'll do all this work in the shaper. So we're set up in the shaper. I have to do it in two settings. It's too long. I have to take this a 1/4 or 1/8 of an inch off of this and profile this down to match this. I will do all four sides or two ends before I taper the rod. At the moment I can grab it because this is square. At the end of the day, this is turned on its edge and is tapered back to here up the other end. And after that I can't really grab it anymore. One of the important things about these big old shapers and the vices is that you're going to make sure that your material is down flat. As you tighten the vise, this jaw will lift up this side a little bit. Even though this is a good fit under here, it still lifts this, and that's what this hammer's for. You just give it a smack and drive it back down so that it's nice and flat. When you start to make your cut, you make sure it's cutting all the way across, nice and square. If it isn't, you beat it with the hammer until it does. So now we're going to start sitting here watching the shaper go back and forth. So we're making the last cut, one of the last cuts on the shaper. This is just a short discussion about shaper etiquette, if you like. These machines are very, very powerful. They have no shear pins. They have nothing in them that's going to stop them if you get it jammed. Something is going to go somewhere. I've seen them bend this tool right around, push the vise off the table. You can break them. So when you're doing these long cuts, one is often tempted to go off and do something else. And it's amazing how slow it is when you sit and watch it, and how fast the time goes by when you're doing something else. It comes to the end of the work, and it ruins the work, ruins the machine, whatever. So when you're running these shapers, yes, they're slow, but you got to keep an eye on them. Not that they're going to screw up, it's just that they're going to run out of space. We're machining it down at this point. If you were to forget it, and it would get into here, it would just either push this out of the way, bend it, or ruin it one way or another. So when you're running a shaper, stay with it. Don't wander away. So here we are at the end of all this with 4 connecting rods. 1, which at the back is original, and 3 manufactured. I know that these rods are every bit or equal to or superior to the original rod. So everything's been done, all the bolts, everything's fitted. The only thing is missing is the key in here for the 2 newest rods, because you need to be able to make this wedge to match the brass. So when you make the brass first, then you make the wedge. So I'm going to put these all away. These get painted, by the way, and start manufacturing brasses. One comment that I'd like to make is that some people feel that these parts should be highly finished. Well, they definitely were not. Maybe on fancy first-class locomotives, the rods were all polished and very shiny. They were probably made out of 4140 or 4340 out of a single billet, or forged. Towards the end of Steam's time, they were made out of billets. But this is a construction engine, and so everything was day late and a dollar short, really. And it was made to do the job, and it was made to do it nicely, but it wasn't made to do it prettily. So this finish is down so that we have no stress notches. Everything's round and ready for service, but it's not polished. It's just going to get painted just like the other 2.
Thank you for watching right to the end of the video. If you're enjoying the project so far, hit that subscribe button so you don't miss out on future videos. Give me a like and leave me a comment. And if this is your first time here, check out these other episodes from the series that you might enjoy.